So the next approach we're going to look at is using variational theory to solve the energy of a helium atom. And so what we need here is a trial function. And there's lots of choices that we could choose, but something based on hydrogen is going to be a good idea. So we know that the wave functions are going to look something like the hydrogen atom wave functions, but because of this electron-electron impulsion term, they won't match exactly. And so sort of the simplest thing we can do is let's take products of hydrogen atom wave functions. And so again, we'll look at just the ground state, look at just a 1s orbital here. And what we want is something we can vary to decrease the energy and find the best possible solution we can get. So what we'll do is we'll use Z, the nuclear charge. We'll treat it as a variable instead of, we know it's actually fixed. It's actually +2 based on the 2 protons. But maybe we can find that there's a difference in the effective nuclear charge because of this electron-electron repulsion. So we're going to treat this as a variational parameter. All right, so our trial wave function is going to depend on our 2 electron coordinates here, R1 and R2. And it'll look similar to our zero-order wave functions for the perturbation theory approach that we had. But now we have something we can vary about this. And just as a reminder, psi1s is going to look like this: 1 over z cubed over pi e to the minus z rj, right? Where rj is r1 or r2. So according to variational theory, we can write out the trial energy for our trial wave function, that E trial is going to be equal to the integral of, call this phi 0 star the Hamiltonian, which we've already written out, phi 0 d tau, divided by the integral of phi 0 star phi 0, because this isn't necessarily a normalized wave function. Now again, this is these are each triple integrals that we'd have to work through, and we'll skip to the results instead of going through all the math of this, and find what the final trial energy is. We get negative 27/16 squared times Hartree. So negative 27/16 squared Hartrees, or if we want to write that in decimals to compare it a little bit easier with our experimental value, minus 2.8477 Hartrees. So this is better than our first order perturbation theory, but still not great because the actual value is negative 2.9 something Hartrees, if you remember right. So better than first order perturbation theory. But we still want to be able to do better than this. So with perturbation theory, we can go to multiple orders. In variational theory, we need a different sort of trial function or something with more parameters that we can vary. And again, if we can decrease the energy, we know we're doing better with variational theory. That's one of the main powers of this approximation method in particular, is that you have a limit, right? You know you're doing better if the energy gets lower, point blank, right? So you can always, if you can find something that decreases your energy you calculate, you did better than you did before. And so one set of wave functions that was derived to give us a better sort of trial function is what's known as the Slater orbitals. And these are based on the hydrogen orbitals, but give us a few more variational parameters. So they're written as S, and they have 3, I'll say quantum numbers in quotes because not all of them are strictly quantum numbers. So we have some normalization constant that's based on N and L. We have R to the N minus 1, E to the minus zeta R, and then we have the spherical harmonics still. Okay, so this is very similar to the hydrogen atom wave functions, but we treat N and, I always have trouble drawing this letter, zeta. So we use N and zeta as our variational parameters. Right, so if we use this, again, we'll just look at the results. The energy that we get, the trial energy, is minus 2.8542 8 Hartrees. And then we can also get out what are n and zeta. N is 0.995. It's close to 1. And zeta is 1.6116. Okay, so the energy did decrease a little bit from our previous trial function. So it's a little bit better. But how can we keep getting better? And so that's what we'll look at in the next video.